Today we will be continue the structure and properties relationships of polymer materials. In the last class I told you that there is a relation of properties with the molecular weight. Molecular weight, with the increase in molecular weight, the properties, different properties increase up to certain molecular weight, but beyond which it levels off. That means beyond certain high molecular weight, the properties increments are not very pronounced. So, this indicates that while you are synthesizing or manufacturing the polymers, you can stop at some point where one can get adequate level of properties. Now, since there is a dependence of the properties on the molecular weight, now we must know the molecular weight, or we must estimate the molecular weight or determine the molecular weight of polymers. And you know, since polymer samples are mixtures of molecules of different sizes of different molecular weights, so we must calculate the molecular weight with the help of averaging techniques. Now, there are bases like number count basis, weight basis, viscosity basis, like this. That means through end group analysis we can count the number of molecules of different sizes present in a sample of polymer, or by measuring the viscosity we can calculate the molecular weight of polymers. Today we will see those expressions for averaging of molecular weights in various ways. Say number average molecular weight. What is number average molecular weight? You know, a relation that if you divide a mass of a material by its total number of moles present, if you divide some quantity of material by its number of moles, then you can get the molecular weight. A simple concept. From that concept, here you see the number average molecular weight can be calculated using this relation. Now, since it is based on counting of number of molecules of any species, say if you consider ith species, in ith species there are n number of molecules having m molecular weights. So, sum of that means each species will can be considered as one fraction, one part. Okay. So, sum of this total mass is the weight of the polymer we have taken for measurement of or determination of molecular weight. In the denominator, you see sum of n, sum of n means total number of moles present in the mass. So, this relation gives you number average molecular weight, and here is a parameter, it is known as the mole fraction or number fraction. Okay. This is very simple thing. If you little analyze this equation, we will understand. Weight average molecular weight by measuring the weight of individual molecules or individual fractions. In the last class I told you how you can fractionate a polymer sample. By dissolving the polymer in a solution, a solvent, you will get a polymer solution. Then by solvent programming you can isolate several fractions having molecules of different sizes or different molecular weights. From there you can calculate this weight average molecular weight. It is the sum of weight fractions of ith species multiplied by the molecular weight of that particular species, and if it is expressed in terms of concentration, then you can have this kind of relations in introducing the concentration terms of ith species. Then if those are converted to number of moles or molecules, whatever it may be, then the expression for weight average molecular weight becomes sum of the product of Ni and Mi square divided by the total concentration C, which is equal to sum of the product of molecules with their mass of each species present in the sample. Okay. This is not very difficult thing, and here you see how these are defined, these parameters are defined, they are explained over here. Another parameter comes Z average molecular weight. So, what we have seen? We have seen that we can get number average molecular weight, weight average molecular weight, and Z average molecular weight. Actually, in this Z average molecular weight, more weightage is given on this product Ni Mi square, because it indicates that the higher molecular weight molecules are weighted even more heavily in this case than in the case of weight average molecular weight. So, this is another averaging technique, weight average technique, but if we deal with this Mn bar or Mw bar, and there is one more averaging technique, I will come later, Mv bar, viscosity average molecular weight. So, with the help of these average molecular weights, we can draw a molecular weight distribution curve. From the molecular weight distribution curve, we can see or we can understand the nature of the the polymer material. We can have some indication about its processability, about its fabrication behavior, about its properties. So, we can have certain indications. Now, look at the viscosity average molecular weight. Here again this viscosity average molecular weight is calculated with the help of weight fraction and weight fraction of one species multiplied by the molecular weight of that particular species to the power a, some exponent is the a small a, and whole to the power sum of this parameter product raised to the power 1 by a. Again, if you split Wy into Ni and Mi, so it is a plus 1. In the screen probably you cannot see properly, it is a plus 1 divided by sum of a product of Ni Mi raised to the power 1 by a. Okay. So, this is the expression for weight average molecular weight. You need to practice of calculating the molecular weights. In the book you can get some data, say weight fraction data, and corresponding to that weight fraction you can have molecular weights. Weight fraction data are provided along with their molecular weights in the book. With the help of those data, you can calculate this weight average molecular weight, viscosity average molecular weight, number average molecular weight, even Z average molecular weight. So, there are certain problems in the exercises given. So, you calculate solve those problems So, you will understand how to determine the molecular weight and then calculate the average molecular weights of a polymer sample. Now, the most important thing comes is the viscosity. Since it is viscosity average molecular weight, how this viscosity average molecular weight data are obtained. That means, how these data can be generated from the polymer sample you have. You have a polymer sample, then if you are asked to measure the viscosity average molecular weight, and how to do. So, you have to take a viscometer. You have in your previous lab classes, you have measured the viscosity of a solvent, viscosity of a solution you have seen, and that can be obtained by measuring the flow times through a narrow capillary. That means, you have to take a capillary viscometer. Could you name a capillary viscometer? No, that is not a viscometer. Oswald viscometer. How it looks? It has a simple Oswald viscometer. Here is a mark, and inside there is a narrow capillary. Okay. You fill this bulb with the solution up to this mark by sucking with the help of a sucker from there. It can have one bulb over here, there is no problem like this. It can have a bulb, so that you can have a more volume of liquid, more volume of solvent, more volume of solution you can take over here. So, this is one Oswald viscometer. So, when this liquid actually passes through this capillary by the action of gravity, you can measure the flow time. You take a stopwatch, you suck the liquid through this limb, raise beyond this level, then you start counting time when the meniscus starts coming down from this level, okay, till it till it crosses this another mark over here. So, that is the flow time for the solvent or liquid that is passing through this capillary. Okay. With the help of that flow time, you can calculate the viscosity. But for polymers, another viscometer is used, that is known as overload viscometer. Overload viscometer. Now, in this viscometer, there is a provision for dilution within this bulb, which is having another limb over here. So, you can see this diagram of this overload viscometer given in textbooks. You can see overload viscometer. There, if you want to measure the viscosity of a solution of varying concentration, if you start with a higher concentration, then you can introduce calculated quantity of solvent inside the bulb, so that you can go for higher dilution and you will have other concentrations or dilute concentrations from the first one. So, this way you can have concentration C1, C2, C3, C4, C5 in grams per deciliter. Okay. So, taking only one concentrated solution, you can have so many measurements of flow time of for so many different concentration. Then the question arises, where is the necessity? Why should you go for that? Every time I can drain out this solution, then fill with fresh solution. Then what you have to do, while you are draining out this thing, then some quantity will remain adhered the inner wall of the apparatus. So, you have to rinse it, again you have to dry it, again you have to fill with the next concentration. So, that is a conversion process. In order to avoid that, if you start with one concentration, just add calculate quantity of solvent for the next concentration, record it and then record the flow time. So, this way you will get the different flow times. So, you can get this relative viscosity from the ratio of the two flow times, flow time for the solution and flow time for the pure solvent. Eta r is equal to T by T0 or eta by eta 0. That is the relative viscosity. It is shown over here. Then specific viscosity is the eta relative minus 1, and reduced viscosity is eta specific by C. C is expressed in grams per deciliter. Then eta inherent ln eta relative by C. So, if you get this flow times for the solution as well as for the solvent, so this relative flow times will help you to get different viscosity terms: specific viscosity, reduced viscosity, inherent viscosity. Inherent viscosity can give some idea about the molecular weight of a polymer, not exactly the exact value of molecular weight, but it can help you to know about the molecular size, some rough idea, approximate idea. Then there is another viscosity term which is written here, intrinsic viscosity. What is intrinsic viscosity? Now, here you have to have some certain concept in order to gather this intrinsic viscosity. Intrinsic viscosity is a viscosity term which is related to eta under third bracket is equal to some constant, say k or k prime, into m v bar viscosity average molecular weight raised to the power alpha or a. That means, this intrinsic viscosity is related to molecular weight, because there is an obvious question, sir, after measuring these flow times, then how can we get this viscosity average molecular weight data? How can you get? So, that is related to this thing. It is actually known as, this equation is known as Mark-Howing equation. It is a famous equation, Mark-Howing equation, which relates viscosity average molecular weight and with the intrinsic viscosity. What are these? These are actually constant parameters dependent on a particular polymer solvent system for a specific polymer solvent system at a specific temperature. Hope you will not forget this relation. Intrinsic viscosity is related to viscosity average molecular weight, and two parameters, two constants parameters there, k prime and alpha or k and alpha. These parameters are known as polymer solvent interaction parameters. What are these polymer solvent interaction parameters? Now, I was telling you in the last class that when you put a solute in a solvent, that solute can enter into solution, can make a solution only when there is an interaction between the solvent and the solute. That interaction depends on the cohesive energy density, of both the components. If the cohesive energy density of both the components are close to each other, then only they can form a solution. That is related to miscibility of a solute with a solvent. Now, here you can extend your concept of alloy, metal alloy. In metal alloy, what we do? We just put a foreign substance in a base metal. If that foreign substance gets becomes soluble in the base metal, we get an alloy. So, there is some concentration limit of that alloying element in a base metal. If it is a solution, solid solution, then we call it an alloy. Am I right? Alloy is a solid solution of a foreign substance in a metallic alloy. Similarly, you can get polymer alloy, solid solution. You can dissolve one polymer in another. So, polymer, if the two components of the two component polymers are highly miscible or one soluble in the other, then we can say it is a miscible polymer blend or polymer alloy. On the contrary, you can see that some polymer can be miscible to a limited concentration, and sometimes one component may remain dispersed in the base polymer, and phases of these two components can be distinctly viewed under electron microscope. That we cannot call a miscible blend, although it is a blend, physical blend. So, this physical blend, alloy and solution, solid solution or liquid solution, all these are formed based on the cohesive energy density of each of the components. What is cohesive energy density? Again, that is related to the bonding force. That means, the residual force fields which is available surrounding a molecule, that force field actually enter into intermolecular interaction in terms of cohesive energy density. If these two cohesive energy densities of the two components are very close, then only they can form a solution. Here, when a polymer is put in a solvent, what happens? These solvent molecules being smaller, that can penetrate inside the bulk of the solid polymer sample molecules. That means, if the cohesive energy density of these two are close to each other, then the solvation energy of the solvent will be sufficient enough to break the intermolecular forces between the molecules of the solid solute or solid polymer. Do you understand? So, here this terminology comes polymer solvent interaction parameter. These are all polymer solvent interaction parameters, and these polymer solvent interaction parameters for one system of polymer and a solvent differs from other system of polymer and a solvent. Am I clear? Okay. This is a very simple thing. So, looking at the cohesive energy density, we can calculate the solubility capability, solution capability of a solvent for a polymer. we can calculate that. We will see that thing later with the help of solubility parameter and molecular weight of the repeat unit of the a polymer as well as the density of the polymer. With these parameters one can calculate the solubility parameter of a solvent as well as the solubility parameter of a polymer. Again these solubility parameters gives a measure of cohesive energy density. So, I think it is clear to you that when a polymer is put in a solvent, if the solvation energy of the solvent is higher than the intermolecular force of the polymer molecules, then only dissolution can happen. And there are thermodynamic considerations also. Free energy of mixing of solvent and polymer should be negative, then only one can get solution. So, here K prime and alpha polymer solvent interaction parameter, if those values are known for a system, then from this relation eta intrinsic is equal to K prime m v bar to the power alpha with. So, this is an experimentally determinable parameter you are getting from its flow times, and these are available from data book at a particular temperature, because the viscosity is measured at a constant temperature, flow times are measured at a constant temperature by immersing the viscometer in a thermostatic bath, all right. So, at that particular temperature you have to find out the values of K prime and alpha, then only you can get this eta r. From eta r you can get these parameters, eta specific, eta reduced, eta inherent. Now, what is intrinsic viscosity? These are none, these are not intrinsic viscosities. How to obtain this intrinsic viscosity? So, you have to make a plot of either ln eta relative by C or eta specific by C. This you can calculate from the flow times against concentration. This is 0 concentration, and you have to measure the viscosity of different fractions or different concentrations. So, what you can get? You can get this say eta specific by C, suppose, for different concentration you are getting this eta specific by C values. Then you extrapolate to this axis, y axis. If you plot ln eta relative by C, it can show you a relation like this. So, this is eta specific by C, this is ln eta relative by C, and you are extrapolating to y axis. That means, at 0 concentration, which is known as extrapolation to infinite dilution. Infinite dilution, extrapolation to infinite dilution. Now, this value actually is known as eta intrinsic or intrinsic viscosity. You understand? Intrinsic viscosity. Why this is necessary? Extrapolation to infinite dilution. You have to have a concept again. Now, you have yes, you are right, to attain ideal situation. Ideal situation means again you have dissolved a certain quantity of polymer in a solvent. Now, there will be interaction between polymer and solvent as well as polymer and polymer. If the concentration is more, that is for higher concentration, there will be more interaction between polymer and polymer molecules, because these polymers actually the configuration of the polymers in a solution looks like this. It remains in folded and curled configuration. It is not that for a linear molecule it remains like this in this configuration, that will be coiled configuration. This is actually called coiled configuration. In a dilute solution, it is expected, or there is the ideal situation, ideal case, where if we assume that the polymer solvent interaction parameter, your cohesive energy density of the polymer and the solvent are almost same. If we assume in that case, the polymer can assume its extended chain configuration in a solution. So, the contact between one polymer molecule with another polymer molecule will be minimized in infinite dilution. Hypothetical situation. In that hypothetical condition of concentration, we can expect that in a polymer solution you can have isolated molecules not remaining touching each other. Why it is necessary? Now, when these polymers are flowing in a solution state through a capillary, if one polymer molecule remains attached to or very close to another polymer molecule, then the resistance offered against flow will be more. Now, here you get one more concept. If you are given two samples of a polymer having same molecular weight, same, say 5 lakhs each for example, but one is linear, another is branched. Two samples, sample 1 and 2, both are having same molecular weight, and the sample 1 contains linear molecules and sample 2 contains branched molecules. Again, if I show you this way, suppose this is the length of the polymer molecule. Now, this length can be shown this way. So, overall length, overall mass of the polymer is same. This is branched, this is linear. You tell me, when you measure the viscosity of sample 1 and sample 2 taking same concentration of these two samples, which one will or the viscosity of the two will be same. You are telling viscosity of sample 1 will be more,
because density will be more.
What you are telling density? You have taken the same concentration. That means the quantity of polymer is same in both the cases. Only difference is one is linear and the other is branched. You are telling it is more viscous, it is less viscous.
Linear will be the more viscous.
So, you are divided into two groups. One group is telling the linear will be more viscous and the other group is telling the sample 2 will be more viscous. Then what is the correct answer? Who can say?
Sir, linear provides the more resistance during flow.
Which way? If I agree with you that linear molecule, linear configuration offers more resistance,
Higher surface energy.
higher surface is same. It is not the question of surface. No, just forget about entanglement. It is the ideal situation. It is an ideal situation where I said that the cohesive energy density or solubility parameter of the polymer and the solvent are very close. I mean to say the solvent is ideal. Known as another parameter theta solvent, and the temperature at which is this is measured, viscosity is measured, is known as theta temperature. That means, it is an hypothetical situation or ideal situation where the solvent polymer interaction is minimum. I have not got the answer to this question, which one will be more viscous. Probably I have to say, because you have just opposing answers. So, I have to solve the problem. This sample 1 will be more viscous. The reason is, when in case of ideal solution or very dilute solution, this molecule is free to gyrate or rotate during movement through the capillary. All right. It is not that true that this molecule always will penetrate the capillary through one end. It is not that kind of good boy. It will take its own course. That means, the radius, you have to think in terms of radius of gyration. So, this system will provide higher radius of gyration than this one. Suppose you are sitting in a chair, now you are sitting in a chair in attention position. So, if you are just told to sit in this fashion for more than 2 hours, you will become impatient. You need to stretch your legs and hands, twist your body, twist your head also, because of the free energy requirement, isn't it? From free energy point of view, you need to stretch your hands, legs, you like to stand also. Now, you think of the volume you require now while you are sitting in an attention position. Now, if you stretch your hands and legs, you stretch your hands and legs this way, if you stand, then the space requirement will be more. So, that is the radius of gyration. In case of branch, that can remain squeezed So, the radius of gyration of this system is less. So, this will be of less viscous than this linear configuration. All right. For all these reasons, actually there was this necessity of extrapolation to infinite dilution here. That means, in order to eliminate all sorts of interaction problems, polymer interaction problems and coiling problems, we can expect that in dilute solution in a theta solvent at theta temperature, this molecule will give extended chain configuration, and then only we can get the proper flow time, proper viscosity, because based on this flow time data and viscosity data, where we are going to calculate the molecular weight, mind it. So, if it remains in coiled configuration like this, curled configuration, then can we get the accurate data? No, it will give you misleading data, misleading result of molecular size. That is why when we like to measure the molecular weight by viscosity measurement, we have to go for this higher dilution or extrapolation to 0 concentration, infinite dilution, because you cannot, because at these regions the flow times will be same for the solvent and the solution are very close, you cannot distinguish. Whereas you have to start with, say you have to start with probably say 0.3 grams per deciliter and onwards 0.3, 0.5, 1, 2, 3, 4 grams per deciliter like this, then only you can get this kind of curve. During your lab class, you take one polymer sample, dissolve in a suitable solvent, say for example take some quantity of polymethyl methacrylate, dissolve in chloroform or benzene, measure the flow times and then calculate these viscosity parameters. Then after plotting you get this intrinsic viscosity, and then from the data book you get the values of this K prime and alpha polymer solvent interaction parameters at that temperature at which you have measured the flow times, and you can calculate the molecular weight. So, here it is shown intrinsic viscosity, either you can go through specific viscosity at C tends to 0 means infinite dilution, or ln eta relative by C in up to infinite dilution. Now, there are two equations which relate this specific viscosity and or inherent viscosity. This is inherent, actually this is actually inherent viscosity, this is specific viscosity, reduced viscosity and the inherent viscosity. Now, this is related to intrinsic viscosity by this relation. This is Huygens equation, this is Kramer's equation, and these are constants, and the difference between these two constants are 0.5. K prime and K double prime is equal to 0.5. Now, one question can arise, sir, if we are unable to measure the flow times of a polymer solution of varying concentrations, but if we measure the flow time of a solution of single concentration, is it possible to get this intrinsic viscosity value, and then can we calculate the molecular weight? This is a question. You have seen the previous case that I told you that you have to measure the concentration, your flow times for different concentrations, but if you do not have that access, if you have only one flow time data, can we get it? Then how can we get this eta intrinsic, this value eta intrinsic? Without extrapolation to infinite dilution, we cannot calculate this eta intrinsic viscosity. Can anybody think of, suppose you know these two equations, Huygens equation and Kramer's equation. With the help of these equations, from a single point flow time measurement or flow time measurement of a single concentration solution of the polymer, is it possible to get this eta intrinsic value? This how?
Substitute K double dash by J dash plus 0.2.
Yes, very good. Yes, it is possible by simple algebraic sum. By simple algebraic sum, you can get it, because you are told that the difference between these two is 0.5. So, you can substitute one of these two constants. So, then by simple algebraic sum you can, because the concentration C value is known, ln eta relative value is known, eta sp value is known, and then you can calculate this eta intrinsic. Once you get it, then from this relation, mark Howing relation, you can calculate this viscosity average molecular weight. So, this is the way how to calculate the viscosity average molecular weight. Now, this is the easiest way to get some molecular weight value of a polymer, provided you get these K prime and alpha values from the data book, because these K prime and alpha values have been evaluated or obtained from some absolute measurement of viscosity by some other technique using samples of known molecular weight. Then in that case you have this MV bar values, then you measure the intrinsic viscosity of that polymer sample. From there you can calculate this K prime and alpha. So, this way this K prime and alpha values have been evaluated from one polymer solvent system. This way you can have, say, polyethylene benzene, you can have polyester DMF system, or you can have polyvinyl chloride tetrahydrofuran. That means, if you put polyvinyl chloride in tetrahydrofuran, it will dissolve. So, or you can take polystyrene and tetrahydrofuran or benzene. So, these values for these polymer solvent system at very different temperatures, those are available in data book. So, those data were computed or calculated by measuring the your absolute molecular weight of those polymers by some other techniques, and taking that polymer sample of known molecular weight by viscosity measurements. These data have been evaluated, K prime and alpha. Now, this slide shows colligative properties and molecular weight determination of polymers by measurement of colligative properties. What are those? The techniques are ebullientiometry, cryoscopy and osmometry, elevation of boiling point, depression of freezing point and osmotic pressure. So, with the help of these techniques, one can get the molecular weight of polymers. So, what is ebullientiometry? You know, this is the temperature elevation and enthalpy of vaporization. So, from these values, and this is the concentration, and this is the number average molecular weight. So, these techniques of ebullientiometry, cryoscopy and osmometry can provide you number average molecular weights of samples. Sometimes we can have, if we have a vapor pressure osmometer, with the help of vapor pressure osmometer one can calculate, one can determine number average molecular weight of a polymer sample. Other than this, there are techniques like ultracentrifugation. Or this ultracentrifugation gives you weight average molecular weight, because you have the experience of centrifuging a dispersion or a suspension or even a solution. You know, due to centrifugal force, so you can separate a suspension or separate solids from an emulsion by ultracentrifugation. So, by that technique one can calculate the molecular weight, or light scattering technique one can calculate, one can determine the molecular weight. This is cryoscopy. So, look at the summary of this molecular weight averages: number average molecular weight average molecular weight, viscosity average molecular weight. Then you draw the distribution curve. This is a distribution curve for different fractions of a polymer solution having different molecular weight. So, where this number average can be located, or the viscosity average can be located, weight average can be located, or Z average can be located. This shows that Z average molecular weight is higher than weight average molecular weight, than viscosity average molecular weight, than number average molecular weight. So, number count gives you the determination of molecular weight of a polymer sample having for low molecular weight species, for low molecular weight polymers. For high molecular weight sample, if you want to measure the molecular weight by number averaging technique, the result will be wrong, misleading. Okay. So, the relation is, you see, look at this thing, mz bar is greater than mw bar is greater than equal to mv bar or greater than mn bar. Mn bar is the lowest, and the ratio of these two parameters, mw bar over mn bar or mz bar over mn bar, is known as the polydispersity. If this is equal to 1, this is known as monodisperse. In that case, the distribution curve will look like this, very sharp, monodisperse. Now, polydispersity can be 2 to 50, suppose. If it is more than 1, it can range from 2 to 50. Higher the polydispersity, then you can have inferior properties of the polymer, inferior properties. Higher the polydispersity means, suppose if you have a polymer sample of say polydispersity 15, means it indicates the broadness of the distribution like this. That means, it is a mixture of molecules of very low molecular weight with medium molecular weight with higher molecular weight. So, this polydispersity value is an indication of processability of a polymer either by solution or by melt technique. Now, during processing, what is the situation we face? When you place some polymer in a machine, then for compounding I mean a polymer product, I told you a polymer product is a mixture of pure or virgin polymer with functional additives. So, this is a polymer product, it contains say colorants, it contains lubricants, it contains stabilizer, it contains curing agent, all these things. Now, polymer is a high viscosity material and these additives are either liquid or solid. So, you have to mix these liquid or solid additives in the form of particle for solid additives, particulate additives, you have to disperse it properly into the matrix of the polymer. So, that is done by working the polymer by shearing force in a machine at elevated temperature. Then only one can get a proper fluidity or viscosity of the polymer, so that it can show an adequate melt viscosity property or flow behavior or rheological property, so that it can be transferred to a mold and then it can fill the mold, so that you can get one particular shape. There it needs a lubricant or some plasticizer. Say PVC, I told you PVC can be you can have rigid PVC as well as flexible PVC. Rigid PVC you have seen, say medicine files, where these your capsules or tablets are packed in some transparent with the help of some transparent plastic sheet, those are rigid PVC sheet. Whereas the same PVC, when it is mixed with some ester plasticizer like dibutyl phthalate, it becomes flexible like leather like. So, plasticized PVC is known as artificial leather. Plasticized PVC is known as artificial leather, whereas rigid PVC does not contain any plasticizer. So, here is a difference between a pure polymer sample and a mixture of polymer sample and a plasticizer of low molecular weight. Now, here why I have told this thing? Now, in a polymer sample, if you see that there are certain fractions of low molecular weight species, that low molecular weight species will act as plasticizer. Do you understand? So, that adds to the processing behavior of the polymer. Thank you.